this lesson, we're going to look at atomic radius as a periodic trend. And we've seen in the previous video that the group trend going down a group is that you increase in size. And that's easily explained by the addition of energy levels, which increases the area of probability with increasing energy level. But the period going from left to right is that the trend is that it's going to decrease, even though we're adding more electrons. And the question is why? If we're adding more electrons, why is it going to be getting smaller? Little background. We've got electrostatic attractions keeping the electrons within the atom. It's the attraction between the oppositely charged electrons and the protons in the nucleus. The larger the charge in a nucleus, the greater the attraction is going to be, because the protons are going to be positive and they're acting as a group. So more protons, more attraction. Also, the closer that the electrons are to the nucleus, the greater the attraction is going to be. So electrons in the first and second energy level are going to be much more strongly attracted than electrons in the sixth and seventh energy level, which are further away. A couple of definitions. Valence electrons are electrons that are in the highest energy level. So when you look at your electron configurations or orbital notations, those electrons that have the highest value for N, the highest value for the energy level, are considered the valence electrons. The electrons that are in lower energy levels we call core electrons. As an example, let's look at a couple of elements. We have chlorine, and if we look at chlorine and look at its configuration, we see that the highest energy represented is the third energy level. And in the third energy level, we have 2 electrons in the S and 5 electrons in the P to give us a total of 7 valence electrons. In iron, this time around, we have the highest energy level being represented by the fourth energy level. Even though it's in the middle of the D block, we still have the highest energy level being represented is the fourth, and it only has 2 valence electrons because the 2 electrons in the fourth energy level. For tin, in the middle of our electron configuration, we have the D sublevel. Tin is on the 5th period, therefore the highest energy level is going to be the 5th energy level, and we have 2 electrons in the S and 2 electrons in the P for a total of 4 valence electrons. Now, effective nuclear charge and shielding effect are 2 factors here that are going to determine whether atoms are going to get smaller or larger. The effective nuclear charge is a calculation that approximates the attractive force that the valence electron is going to feel from the nucleus. And in this equation, Z effective is the effective nuclear charge. Z is the number of protons in the nucleus, and since the protons are all tightly packed in the nucleus, we treat that as one particle, even though it's multiple particles. We treat it as one particle with a large charge because of the concentration in the center. S represents the number of core electrons, and since the repulsive forces of the inner electrons, the electrons are negative and they're going to repel each other, these core electrons are going to block the attraction of the valence electrons. I put that in quotes because they're not actively blocking it, but in a sense, it's causing the nucleus, the protons in the nucleus, to not have the attractive force for the outermost electrons as much, as if there were no electrons in between them. We call this blocking effect the shielding effect. And let's look at an example here. If we look at the 2 electrons that are in the first energy level, there is nothing between them and the nucleus. For that reason, the strongest attraction is going to be between the nucleus and the very first energy level, because there's nothing in between them. When we get to the second energy level, we have the first energy level electrons between the nucleus and the second energy level. So those first energy level electrons are going to repel outwards a little bit those second energy level electrons. The effect isn't all that great because it's only 2 electrons in the first energy level, and they are also further apart. When we get to the third energy level, we see that the second and third energy level are a little closer together. The repulsion is going to be a little bit greater, so that shielding effect is going to be enhanced somewhat. We now have the first and second energy level electrons between the nucleus and the third energy level, reducing the attraction. We get to the fourth energy level, it becomes even greater. Now, I wasn't able to show it, but there are actually 18 electrons between in the third energy level. So we have a total of 28 electrons in between the nucleus and the fourth energy level. So our shielding effect is getting greater and greater. Think of it as like sitting in the front row versus sitting in the back row in class. Those people in the front row are able to see the board much more easily than the people in the back row, because the back row has people in rows between them that makes it harder for them to see the board. In a sense, that's kind of what's happening here with the electrons. The electrons in the outermost energy levels, the attraction between them in the nucleus is being reduced because of all of the electrons building up between them in the nucleus. So those core electrons are the electrons that are causing that reduced attraction. Let's look at how this works with period 3. In period 3, we start with 10 core electrons. The first and second energy level are filled with the S and P, in the second energy level having a total of 8, and in the first energy level a total of 2. So we've got 10 core electrons. So in our calculation for sodium, we are going to have 11 protons as our Z. We're going to have 10 as our core electrons, and the effective nuclear charge then is a value of 1. This is not an actual measurement value. This is just a relative value that we can use to compare. If we go up 1 proton, we now get to magnesium, and magnesium has 1 more proton. It's got 1 more electron. That electron is going into the third energy level. We still have 10 core electrons, but we've increased the number of protons up to 12. And our effective nuclear charge now is 2, which means that magnesium is going to have a greater attraction for its valence electrons, the electrons in the third energy level, than what sodium had. The effect of that is that magnesium is going to be smaller than what sodium is. If we continue on, we can see as we go across the period that we keep adding a proton and an electron, but the core number of electrons continues to be the same. So our effective nuclear charge as we go across the period is increasing. And that increasing effective nuclear charge is going to cause the atom to be smaller and smaller and smaller.